All right. So now we will move on to the should be the third phase, right, of this lecture. We're going to start talking about GPU programming. This is a very important part of this course because as this is quite different from the CPU program, right? We have to know the architecture of a GPU, and we have to know entirely different parallel programming API. And the whole GPU programming is also under it's under a broader area of heterogeneous computing. Okay, so before we jump into CUDA, right, the language we're going to teach, we will just first overview what is heterogeneous computing and uh, what's the role of GPU for parallel computing. Okay. All right, so we have two parts. We will first talk about heterogeneous computing in general, and then have an overview of the basic architecture and the role of GPU. Okay. All right, so I think you should still remember this, right? We mentioned this in the very first lecture in our course. So you can see right now we are moving to the last stage about the heterogeneous system, right? We already talking about OpenMP, MPI, and then next we will talk about CUDA. Okay, and for distributed system, actually will be the last part of our lecture when we use big data and deep learning as example of distributed computing. Okay. So what is heterogeneous computing, right? Its definition is very general. That means whenever you try to use multiple types of computing units to run your program, then you are doing the heterogeneous computing. So it's not limited to CPU, right? You if you don't use CPU but use the other two type of computing unit, that's also a heterogeneous computing. So it doesn't necessarily involve CPU or GPU. But of course, the most commonly use case today is to combine CPU and GPU for heterogeneous computing. But I think FPGA, right, or ASIC right now is also quite popular now. Okay, and the heterogeneous computing, right, can happen in any scale, as small as just a phone or even an embedded system. They might already have the power of heterogeneous computing because you can install, different kinds of processor chip on that embedded system. But it can also be in as large as the scale of a supercomputer, as we mentioned, right? Almost all the top 10 supercomputers um, possess the heterogeneous computing power by installing GPU or other coprocessor or accelerators. Okay, and we said that this is heterogeneous computing is very popular today because it reached the best of two worlds, right? One is CPU, which is has very good programmability and flexibility, but its performance is bounded, right? Because its architecture is too complicated. Okay. On the other hand, we have those accelerator, right? Those all kinds of specialized processor. They are extremely powerful, but they are sometimes have to ad hoc programming, or you don't have so many programming tools or good programming environment. So its ability also may be limited, like a single processor, right? So, however, for any application or any computing task we want to solve, they may consist of different type of computing, pattern or behavior. So some of them could be better fit for CPU, others may better fit for other processor. So if we use heterogeneous computing, then we can reach the best of two world, right, by sending the code to the proper processor, right? Okay. So for of course, right, for this course, we will use GPU and CPU as example. And in general, right, even for the GPU server we have for this course, it's actually an extension of the commodity server, right? That is, you have a CPU and you have a GPU, but they are actually running and installed it separately. That means for GPU, especially, it has its own GPU core, it has its own GPU memory, and it doesn't even get controlled by the fully controlled by the operating system. So it's like a system within a system. Okay, so you have CPU, you have memory, all those basic, right, needed computer component. But then you also have GPU, you have all the component you need within the GPU card. Okay? And they are simply connected by some system bus, right, like the PCIe bus. So the GPU and the CPU basically can run independently. Okay? So that's one way to provide heterogeneous computing, right? By combining those two type of computing unit loosely between each other. But you can also, but there are also the other type of system that is more tightly coupled of the two different or multiple computing units. That kind of system is what we call the heterogeneous system architecture, HSA. Okay, so it is a hardware solution. It's a computer architecture, and the main goal of this computer architecture is, as showing over here, we want to provide a unified and coherent memory among different type of computing units, such as GPU and CPU. Okay, um, and this is hard, right? Why it is hard? Because different computing units, they may have different control logic to the memory, and more importantly, they might computing in a different scale of speed, right? For example, GPU is way faster than CPU. So if you need to coherent, right, or coordinate between two computing units with completely different speed, then you might suffer from that sort of issue. Not only it's you have a more complex architecture, but also you have to address some of the synchronization issue, right, between those two types of hardware. Okay. However, you have to coherent that, because we have those data coherence or consistent issue, right? If they are directly connected to the same memory, then that means they both have the ability to concurrent override or modify the memory content. So you need to have some locking mechanism or synchronization mechanism, right, to resolve that issue. So that becomes a unavoidable problem. Okay, so it is very hard. Okay, however, if you can achieve that, then what's the benefit? The benefit is you can greatly reduce the memory copy time, because as we after we introduce GPU programming, you will know that memory copy or data transfer is the main bottleneck for GPU or for any accelerator. Okay, even for our, remember we have a optimization chapter specifically for GPU. In that chapter, it's all about memory optimization, how to reduce or hide the memory transfer time. And the memory transfer time is a major bottleneck, right? In the simple architecture we usually have, right? Because GPU and CPU, they have their own memory. Okay, so in order to let the GPU to compute the content from the CPU, you have to first copy the content from main memory to GPU memory, and that's time consuming. Okay, so that's why people are interested in HSA. okay, because they want to, and it's probably the only way to fully address this issue. But on the other hand, you will face those coherence problem. So there's always some trade-off between them. Okay, all right. And also, SHA is a hardware solution, so that's why for us especially, we are more interested in solving the problem for the commodity server, right? Okay, and here is example for HSA. Okay, so today there are already quite a few processor or computer system built on HSA architecture. And the APU from AMD is one of the example. As you can see, it's a very tightly coupled processor, which include GPU core and CPU core on the same chip. And more importantly is those two types of core, they can both directly access to a memory controller. So that means they have a unified memory among those two processor cores. Okay. This is just example, and if you look at the top 500 list, you can also find a couple of supercomputers using this kind of a processor. You can find them by, if you see that the supercomputer only has CPU processor but doesn't have an accelerator, but it can still reach a very high performance, then that means it's very, very likely using this technology. So actually it does have accelerator, but the accelerator is already very tightly coupled with the CPU. So he might even be able to achieve higher performance than just using, just plug in the GPU unit. Okay. All right. So that's just a brief overview about the heterogeneous computing before we jump into GPU. Okay. All right. So what's GPU? I think all of you know, right? GPU is a graphic processing unit, and every computer has it because we use it to render the image and output the result to our screen, right? And we all know that GPU is based on the Cindy architecture. So that's why he can have high throughput, and he can explore data parallelism from image processing to make the rendering really, really fast. Okay. And because he used the Cindy process architecture, so the number of cores, right, within a single GPU card can reach over even thousands. Okay, and moreover, um, you will see that the number of concurrent threads that can be run on those core or the whole GPU is even more than the number of physical core. So I think you probably know that for CPU we have the hyper-threading technology, right, which allow a single CPU core to run two concurrent threads at the same time, but that's only two. For GPU, a single GPU core can use a very similar technique, but run maybe 10 or 16 threads at the same time. So you can see the concurrent threads will be even more than the processor or the cores you have. So the parallelism is even higher. Okay? So that's why it can generate a very, very high performance or throughput, right? Because you have so many cores within that card. Okay? And of course, in the past, the GPU market is dominated by two companies. One is NVIDIA, which is still very well known today. The other is ATI. You probably haven't heard it before because it got bought by the AMD. Okay, so but still, we know the GPU market is right now pretty much dominated by those two vendors, and NVIDIA is the more dominant one right now. Okay. So CUDA and the material we talk about in this course, many of them are based on the technology and the tools from NVIDIA because they are specialized design for the NVIDIA GPU, which allow we to reach the best performance and the most control of the device, right? All right. And so for GPU programming, although GPU is very old and GPU programming seems very new, but actually you can do GPU programming on any of the GPU card. Okay, even for the card that can use to just render the images. Okay, so the difference is that um, the GPU power is actually always there, right? It's always very powerful. But in the past, it is only used for image rendering. But today we find that many of our computation could also has the could be also accelerated by GPU because they have data parallelism as well, especially for those matrix operation like deep learning, etc., or some data processing application. The one with for loop without dependency between iterations, right? All those computing tasks can easily be accelerated on GPU. So people start thinking about or try to expose the power of GPU to general purpose computing. So the GPU designed for rendering is what we call just regular GPU. But the GPU today designed for general purpose computing, not image rendering, is called the GPGPU. Okay, so they are both GPU, but and the architecture similar. But for GPGPU, sometimes he has some other more specialized design hardware, and more importantly, he has a probably better software support uh, or library for general purpose programming. Okay? So as you can see that we said that even for the earlier GPU, you can already run some general purpose program on it. But without the proper tools, what you could do is to use those library that used for image rendering, like OpenGL and DirectX. So their API is designed to write a rendering computing job, not a for loop or some general purpose function. Okay, so it's very hard and difficult to do the programming. Okay, so that's why for general purpose GPU today we will rely on CUDA or OpenCL or other libraries that is developed to expose the power for general purpose computing. Okay, and CUDA is the one we're going to teach in this class. Okay, all right. So this is what we mentioned before, right? So before we do any programming, you have to have understanding of the basic performance and architecture of your computing system. So this is, of course, right, for this course, we will only care about the commodity solution, right, with CPU and GPU connected by the PCIe bus, not the case for HSA. Okay. So this is the system bus or the architecture that connects CPU and GPU. And all you need to know is that, as you can see, the PCIe bus is quite slow. Okay? Of course, this data is out of date, but even for Gen 4 or Gen 5, this number probably only grows to maybe 72 gigabytes, while within the GPU, it used to be only 35, but now it's over even 1 terabytes. It's increased even faster than the PCIe bus. So the bottlenecks actually become worse, not better. Okay. The second thing is the size of the memory. So for main memory, we know, just regular computer, we probably already can have up to 100 gigabytes. Some server can even install up to 1 terabyte memory. It's not uncommon. Okay, but for GPU card, it used to be just maybe 40 gigabyte, but even to today, it only grows to up to 64 gigabyte. So the size of a GPU is way much smaller than the main memory, and so that limits the amount of data we can process right by GPU. So this is another performance bottleneck or another bottleneck for GPU programming, and you will certainly encounter this problem in your next homework. Okay. All right. So here's an overview, right? We look even deeper to the inside of a GPU. This is a general GPU architecture for GPU. And as you can see that GPU have so many cores. So he also needs a scalable architecture to manage those cores or coordinate those cores. So what he has is a hierarchy structure, right? So a GPU card actually consists of many string processor, okay? And each string processor work independently. And each string processor has many core. And those core actually, we didn't plot here, but we will also talk about it, introduce it later on, that those cores are actually coming from a set of SIMD processor. So actually, SIMD processor is within the string processor. Okay. So no, this hierarchy help us to be more scalable because they could work independently. Okay. And for memory, it's the similar things. So the memory, no, we have global memory outside, allow every single core to access it, and the space is relatively larger compared to those local memory, but it's slow, right? Because it's far away from those core. So data access is important. So that's why it has a per block shared memory on each SM that can share and only accessible by the core on the SM. Okay, so it's faster but smaller, and the access scope is also more limited. And certainly for each core, it has its register. So you can have some local variable that can only be accessed by a single thread. So for memory, you also has architecture, a hierarchical architecture like this. So that's why later on when we introduce the API, you will see the API is basically abstract this whole system architecture for us. Okay. So we'll just finish this and talk about the rest in the next lecture because we're running out of time. So this is the zoom in for string processor, as I mentioned, right? There's more cores, and you will see this SFU over here. So this is actually a single SIMD. Okay. So we'll talk about the detail later. Okay, when we go to the the chapter for introducing the GPU architecture. Okay. All right. So we will stop here, and next week we will quickly wrap up the rest of the slides and start talking about CUDA.